Welcome. Today we'd like to talk a little bit about the Zynq 7000 all-programmable SoC and low-power solutions. What is important to a customer with regards to power varies with their application. There are two main categories, line-powered and battery-powered applications. For line-powered applications, customers are frequently interested in how do I go about reducing my power consumption. And with regards to that, by being able to reduce my power consumption, I can reduce other things, such as I can go to a smaller power supply. I can go to less heat sinking. I can go to fewer cooling fans or smaller cooling fans, or possibly even eliminate cooling fans. I can go with smaller packaging. And all totaled, I can get reduced costs because of being able to eliminate this cooling. For battery-powered applications, frequently customers are interested in how do I go about increasing my battery life, or can I use a smaller battery and get the same battery life? Part of this, I'd like to reduce that battery weight. I'd like to get smaller packaging by eliminating battery, and of course you always have heat dissipation challenges. Both types of applications are looking at increased reliability. Generally with lower power, you get lower heat and increased reliability. And how do I go about reducing my total bill of material costs? In the case of line-powered operation, being able to go with smaller heat sinks reduces costs. Similarly with battery-powered operation, going with a smaller battery, smaller packaging can reduce my bill of material costs. Well, let's look at different power reduction techniques. I'm going to start out with the programmable logic side of the Zynq 7000 all-programmable SoC. For programmable logic, first and probably greatest thing to look at is my resource utilization. Is there a way to go to a smaller part or simply reduce the amount of logic that I'm utilizing in the existing part? By doing so, generally I'll be able to reduce power consumption. So one option is partial reconfiguration. And with partial reconfiguration, the idea is that, hey, I may not be using all of my logic functions at the same time. I might need logic function A for a particular application, and then I might need logic function B for a different application. Currently, in an implementation, you may have both sets of logic in the programmable logic up and running. What if you can go with a smaller part and just run logic application A, and then sometime later swap it out and put in logic application B? The net effect is I'm going with a smaller part, I can get reduced cost, and I am saving on the static power consumption that might be used by logic that is just sitting there idle. Next option is one of frequency scaling. Take a look at your application. Is it necessary to be running all of your logic at full speed all the time? Is it possible to gate off unused blocks? So if you have an application that, again, is performing a particular function, but only needs that function for a specific amount of time, why not gate it off completely when you're not using it? Next phase is basically saying, I don't need any of the programmable logic for a particular amount of time, so why not completely gate it off? Maybe my processing system just needs to do some calculations. I don't need the programmable logic at that time. Next level would be, after turning off the programmable logic, we can put it in data retention mode. Data retention mode is turning off all the clocks to the programmable logic and then reducing the voltage going into the programmable logic to the data retention level. This reduces static power consumption. And then finally, in some applications, you may be able to completely turn off your programmable logic while leaving your processing system running. On the processing side, as we will demonstrate, CPU application loading can make a significant difference in your power consumption. So can you change your application to reduce the amount of CPU loading? Similarly, can I reduce my loading so much that I can go to a single core? can I go and reduce my loading so much that I can start doing frequency scaling, doing things like moving from 667 megahertz down to 333 megahertz, or even 222 megahertz, or even 33 megahertz? Can I take my application and keep it in an idle state as long as possible? In other words, no processing occurring. And then finally, for some applications, you may discover that you can put the processing system in a complete standby mode. Now let's look at some of these in a little more detail. CPU loading and CPU idle functions are really dependent on your application. They're not really operating system functions. The intent here is how much can I reduce my compute-intensive tasks, and how much of the time can I reduce those compute-intensive tasks. Now, there are a variety of techniques to do this. One of the most obvious is avoid polling of devices and registers. Instead, wait for an interrupt. And the wait for interrupt instruction, or WFI instruction, is the way to go. And there are ways to use this indirectly. So, for example, you can append waiting for a signal. That signal may be coming from a peripheral, from a timer, or even from another process in your system. But the important thing is to be able to maximize the time you are in this state. With regards to CPU frequency scaling, or even scaling down to a single core, this does require an operating system call to change the state of the system. Obviously, you're going to be able to reduce power, but you have to be able to accept the performance reduction. And in many applications, it is possible. And it is also possible to do this frequency scaling on the fly. Typically, where we see frequency scaling going on is where you are able to move into a maintenance mode. So, for example, you may be doing a heavy set of computations. You need to be running at maximum processor frequency. And then later on, you are going into an idle state. You've basically displayed your results. You're now waiting for a peripheral input or keyboard input. So why not scale down your frequency? Power on suspend or standby is your next state option. It does require an operating system call to enter, and there are a series of steps for the operating system to go into the suspend state. So this means that the suspend state takes a little bit of time to get into and a little bit of time to get out of. The steps that the operating system goes through is, first, it freezes tasks and processes. It gracefully shuts down peripherals. It turns off the peripheral clocks and the peripheral PLL. It'll place the DDR memory into self-refresh. It'll turn off the DDR controller and the I/O pins. Next, we want to reduce the processor clock rate, put it into PLL bypass, turn off the processor PLL, and then finally the processor enters that wait for interrupt instruction. To resume is basically a reverse of the above steps. Now let's take a look at the demonstration that I'll be showing. First, I'd like to point out the Xilinx Power Estimator is the authority for information when it comes to power. The tool is incredibly powerful, pun intended. It allows you to select the device, the temperature that it's going to be operating at, the speed grade, and other characteristics such as the heat sinking that's available, the amount of air that's flowing through the system. You're able to set the what is being utilized in the programmable logic, as well as what is being set in the processing system. Now with the demonstration, what will we be showing? On the processing system side, we'll be showing CPU loading, CPU frequency scaling, how to move into the idle state. With the programmable logic, we'll be showing programmable logic utilization, frequency scaling, and what happens when you gate everything off. We're also going to show two separate demonstrations. One is with a boot of open source Linux, And with that, we'll be able to control both the processing system and the programmable logic in terms of utilization and clock frequencies. And then we're also going to show a boot to Ubuntu and how you can create your own application, run it in Ubuntu, and again, see processor utilization as well as power consumption. Setup consists of a Zynq ZC702 board. Connected to that board is a laptop running a user application that we provide. Connected also is a mouse and optionally a keyboard. And then finally, a monitor. Within the programmable logic, we have implemented a design. It consists of 240 PicoBlazes that can be operated up to 200 megahertz. And these PicoBlazes optionally can be driving shift register, toggle flip-flops, and accumulators. Now a little bit about the display that you'll be seeing. First, when it comes up, you'll want to select the COM port you're communicating with to the development board. Next window is the configurations that are requiring reboot, and so you will see us start out with open source Linux and then reboot to Ubuntu on top of open source Linux. The yellow windows allow you to select key characteristics both for the processing system and the programmable logic, such as frequency and loading. On the right-hand side, you'll have a pair of windows where you can select individually and examine the power regulators that are supplying the power to the board as well as the Zynq part. On the lower left-hand side, you'll see a console. So when the system is booting, you can see the activity that is occurring. And then on the left-hand side, in blue, are our power windows. You get several different graphs. One graph will show the total system power consumption. Another graph will show the total programmable logic power consumption. And then you have additional graphs that show power consumption for the processing system. And then finally, at the bottom of the screen on the left-hand side, we have a window that shows CPU utilization, and you can see the activity between the two cores. In the demonstration, you'll see us start out with the CPU frequency at maximum 667 megahertz, running the Spec 2000 benchmark on both cores. So you'll see them 100% utilized. Programmable logic operating at 200 megahertz and 100% utilized. And then we're going to go through a couple steps of dropping the programmable logic utilization down ultimately to a frequency of 0. So basically we've clock gated it off. Then we're processing system. We'll start out again with the two cores fully active and loaded, move them to one core just running a benchmark, the other one being in idle, then moving the system to idle, then dropping the processing frequency down as low as 33 megahertz, and having the CPU idle and going into the lowest power state. And then we'll demonstrate what happens after we've booted Ubuntu and look at how the power consumption appears with an operating system and the Ubuntu desktop and a user application such as the Mandelbrot demo. Now, kind of looking at it from a measurements viewpoint, these are numbers that were pulled from the Xilinx Power Estimator, and I'm showing you what it looks like when we do different types of power management techniques. So, first, consider us at 100% utilized. And now we've taken the CPU and we've dropped the loading to 50%. When we do that, we reduce the total processing system power consumption by 34%. If we move both cores to an idle state, basically just doing simple background tests, probably less than 5% utilization, you'll see now the total power reduction is 60%. Next, if we take those idle cores but drop the processor clock down to 33 megahertz, bypass the processing system PLL, we are now have a power reduction of 74%. And then finally, moving into that standby state, you can reduce power by as much as 96%. I'd also like to point out that if you do elect to use our low power parts, the static power consumption for both the processing system and the programmable logic is reduced by 50%. Well, now let's go ahead and take a look at our demo. I've started the Power demo application on the PC. I've selected the COM port for this board, which is COM4. I am now turning on the ZC702 board. It takes just about 6-7 seconds to boot the open source Linux. And when it's ready to go, we get a green box for apply. I click apply, and we now can start seeing the power consumption for the system. Now currently we are running the processor at 667 megahertz, and the processing loads are at idle. I'm going to take the system up to full utilization with running benchmarks on both CPU cores. We'll run the programmable logic at a full 200 megahertz. We will have utilization at 100%, so we have those 240 PicoBlazes implemented and running. We'll turn on the PicoBlazes exercising accumulators, shift registers, and toggle flip-flops. And now I'll click apply. Takes a few seconds. You'll see again, looking down at the CPU utilization window, both cores are 100% utilized, running the benchmarks. Looking over at our power consumption in the system, you'll see that the processing system cores are consuming about 621 milliwatts. The DDR memory interface, as well as the external DDR memory, is consuming about 540 milliwatts. IOs around 18 to 20 milliwatts. Total power consumption for the processing system plus the DDR memory is right about 1.2 watts. And the programmable logic, fairly heavily utilized, consuming about 1.5 watts. Total system power is at 2.7 watts. Now earlier I talked about different ways of scaling power, and so the first thing we'll do is scale back on the programmable logic. Possibly we can drop down to, let's say, 100 megahertz and maybe only 50% utilized. And then we can take a look at the associated power reduction that occurs when we reduce both the utilization as well as the clock frequency. Next step might be to take the programmable logic all the way down, turn it off. Again, I'll click apply, and again you can see the associated power reduction with the programmable logic. And at this point, the programmable logic power consumption is just the static power for that programmable logic area, which is roughly about 140 milliwatts. In a similar manner, I can also step down the processor utilization. And let's drop it down to a single application running, which will be running on a single core. And you'll see that we go from roughly 580 milliwatts. Looking down, you'll see that one core now is at 0% utilization. And we drop to about 490 milliwatts, so roughly 100 milliwatt savings. In the same manner, I can now go and put the CPU into an idle state, click apply. You'll see the second core utilization go down to 0, and our processing system core's power consumption has dropped to about 380, 390 milliwatts. So again, about another 100 milliwatts savings. Now you might think idle's lowest power consumption, but I can then drop my processing core frequency down to 33 megahertz and click apply. The core frequencies have now been reduced to 33 megahertz. The PLL has been bypassed. We're running directly off the external crystal frequency, and the PLL has been disabled for the processing system. And as you can see, the processing system power consumption has dropped roughly another 100 milliwatts down to about 216 milliwatts. The next step that one can do is put the system into full standby. At room temperature, your power consumption can drop down as low as 45 milliwatts with a regular part, or with the low power part, as low as about 20 milliwatts. At this time, we have booted open source Linux with the Ubuntu desktop. If you look at the power consumption, you'll see that for the processing system logic, we're consuming about 400 milliwatts. The processing system, the memory controller, as well as the external DDR memory, we're consuming about 530 milliwatts. PSIO, about 19 milliwatts. Total power consumption for the entire processing system, plus the DDR memory, is about 960 milliwatts. In the programmable logic, we just have a display controller implemented, so the power consumption is about 450 milliwatts. As I mentioned, we've got the open source Linux booted and the Ubuntu desktop up and running. I've also started the Mandelbrot demo, but have paused it. And if you look down at CPU utilization, you'll see that both cores are pretty much idle. We will then start the Mandelbrot demo. And you'll see now that the two cores, their utilization has gone up to roughly 100%. If you look at the processing system cores, they're consuming about 610 milliwatts, or roughly 200 milliwatts additional. And you can see in the graphical display the associated power increase. So if you'd like to find out a little bit more about Zynq power management techniques and the documentation that we have available, we'd like you to visit Zynq 7000 APSoC Power Management on our wiki. We have a collection of technical documents also available on the wiki. They're all around power management, including how to go and install the power demo, how to go and control frequency scaling, how to control the programmable logic, all from the processing system. And these are links that are available to you, and documents that are available to you, as well as design examples that are available to you. So to wrap up, there are multiple techniques that are available for processing system power management. And these techniques at the highest level basically focus on how can I better utilize my processing resources, including both the processing system and the programmable logic. How can I go about frequency scaling to reduce power consumption? How can I do clock gating? All of this is enabled by Xilinx design tools and the hardware that we provide you. And again, you can find more information on wiki.xilinx.com. Thank you.